G'day, how you going? Let's conclude our electrochem unit here with today's lesson called Spontaneity, Gibbs-free energy and cell potential, where we're going to investigate reaction spontaneity by linking the concepts of Gibbs-free energy and cell potential. So we've been talking about reaction feasibility in terms of our cell potential values, and we've been saying that it needs to be positive in order for the reaction to be feasible, but this only implies that the reaction is possible, and we've predominantly been looking under those standard conditions there. But last time we talked about non-standard conditions, the fact that these are redox equilibriums, so they're going to be influenced by the same factors that will affect any equilibrium: concentration, temperature, and pressure. And if we shift that position of equilibrium, we are going to affect the cell potentials and the reduction potentials accordingly. So there's a general rule that we can use to predict if a reaction will occur under non-standard conditions, which states that generally if our reduction potentials differ by more than 0.3 volts, we would say it's highly likely to occur, and we could predict that the reaction would take place. However, this is just a rough guide. Lower differences may still react, but it gives us a good rule of thumb that we can apply, which we can do right now, early on with a question. Would you expect a redox reaction to occur between the following two half cells at non-standard conditions? So consider what our reduction potentials will tell us about what is being reduced, what is being oxidized, calculate the cell potential, and apply our rule if we were at non-standard conditions, and tell me if it's likely to occur or not. What do we have to do? Well, first we've got to work out what will be reduced and what will be oxidized. We've got a more positive value up the top here, so that's very much going to be our reduction reaction because it's the better oxidizing agent. And our more negative value there, that's very much going to be oxidized, implying it's our better reducing agent. We could apply our clockwise rule here because we got our reduction potentials in decreasing reduction potential. And look, we're making a clockwise direction. So at standard conditions, that would imply that the reaction would be feasible. But recall, we are at non-standard conditions. And just a reminder that the little clockwise rule only works if they're in decreasing reduction potential values. So look, let's put some numbers to this. Let's get the standard cell potential by getting the reduction potential and adding that to the oxidation potential. Well, we said that our top one there is going to be the one that will be oxidized. Sorry, the top one there with the more positive, that will be reduced more accurately. And our one underneath, more negative, will be oxidized. And we're going in the reverse direction. So we've got to flip that sign to get a value. When we plug all this into our calculator, 1.52 minus 1.36, we get a value of plus 0.16 volts, which, applying our threshold here of 0.30 volts, we would in fact conclude that the reaction, we could not predict with confidence if the reaction would occur because our calculated standard cell potential is less than that 0.3 volts. But again, just a general rule, lower differences may still react. So when we're talking about feasibility, we're talking in terms of spontaneous changes. A change that occurs naturally is referred to as a spontaneous change, implying that once the reaction or once the change begins, it continues by itself unassisted. Now, don't get this confused with it necessarily being a rapid change. It can be a very, very slow change and still be spontaneous, but a spontaneous change is just able to occur. And once it does occur, it continues unassisted. So what this might be ringing some bells and reminding you of is the concept of Gibbs-free energy. Now, we've got a whole video on Gibbs-free energy. If you want a big deep dive into that, that's there. We're just going to quickly introduce the core concepts and then link it to what this implies about our cell potentials that we've been looking at. So very briefly, our Gibbs-free energy can be thought of the maximum amount of energy available to do something, to do work. So when we talk about work, we're talking about doing something useful, driving a change to occur, which in this instance, we're going to be talking about a chemical change, a chemical reaction. So we need energy available. There needs to be energy free to do this useful work. So that's where our sign of delta G will tell us if this energy is available or not, and therefore dictate if the reaction is spontaneous. So let's go through the three possibilities we can have. Either delta G is less than 0, it's a negative value, and we would say that therefore there's energy available to do work, and it would be a spontaneous, feasible process, and we can also use that word exergonic to describe that. Conversely, if delta G is greater than 0, it means that we have a positive value, and therefore the reaction is non-spontaneous or not feasible, and we can refer to that as endergonic. And then our third option is where delta G equals 0, and that implies our reaction is at equilibrium, where there will be no observable change. So when we're talking about our redox, we've also, as we just talked about, a minute ago, we've also got our values for our cell potentials that are going to imply if the reaction is feasible / spontaneous as well. So we need to make sure our values for delta G and cell potential are consistent with each other to have these inferences about the spontaneity of the reaction. So let's have a look again at the 3 possible outcomes we can have. So we said that if delta G is negative, we have a spontaneous reaction. So therefore our cell potential needs to be positive. We've been talking about feasibility for our cell potential always needs to be positive. So therefore if delta G is negative, our cell potential has to be positive and we have a spontaneous reaction. The opposite of that is that delta G is positive, therefore the cell potential is negative, and these both imply that we have a non-spontaneous reaction. And if they're both equal to 0, then we have a system that is at equilibrium. So really importantly, these 2 factors are mathematically linked because the signs always have to be consistent with one another, like we've been saying. So we've got an equation here which states that delta G is equal to minus N times by the cell potential times by F, where N is referring to the moles of electrons transferred and F is the good old Faraday constant with our value there. So let's think about this minus sign. Well, these signs are inversed, right? So if I've got a positive value for my cell potential, I need to have a negative value for my delta G. You're always going to have a positive number of electrons transferred. You can't have a negative number of electrons transferred. And then your Faraday's constant is also a constant, which is the positive value. So we've got to make sure those signs are flipped. Same thing, if we've got a negative cell potential, we're going to make sure we've got a positive delta G. So a negative times a negative is going to be giving us that positive value over there. What have we got here? Minus sign necessary in equation to ensure that our delta G and E are consistent for spontaneity. Gibbs-free energy, as an energy, has units of joules, or commonly kilojoules or kilojoules per mole. But we've got units up here of moles, we got volts, we got a Faraday, which is coulombs per mole. You might go, hey guy, where's the joules coming from? What's the deal? Let's talk about it. Let's extrapolate some units. As it turns out, 1 volt is 1 joule of energy per coulomb. Physics. So we can use this to show our units cancelling out to give our joules for our delta G. So let's just have a look at the units. I won't worry about a sign there. We got number of moles in mole. We're multiplying that by the voltage, but hang on, we just said a volt is a joule per coulomb. So let's substitute that in there for our voltage. And then our Faraday's is a coulomb per mole. What we have is we have some stuff cancelling out. Our moles can cancel out, our coulombs can cancel out. And we do in fact end up with delta G having the value of joules. Just be aware that you might have to convert to kilojoules or kilojoules per mole, depending on the kind of question that you're given. But look, let's apply that. It's just a bit of a plug and play type question. I've given you a redox equation. I've given you a cell potential, Faraday's constant, 96,500. Why don't you pause and see if you can give me a value for delta G there. All right, let's do it. So we have our equation, which is delta G is equal to minus N times by the cell potential times by Faraday's constant. So how many moles of electrons are being transferred? Well, we're going from Zn to Zn2 plus. We're going from Cu2 plus to Cu. So we have to be transferring 2 moles of electrons. We could write out each of those redox, each of the reduction and oxidation half equations, but it's very much going to be 2 moles of electrons being transferred. So we can plug a 2 in there. Our cell potential was given to us, cell potential of 1.1, that classic zinc copper galvanic cell, and then Faraday's constant is a constant, 96,500. So like I say, just a bit of a plug and play here. So minus 2 times 1.1 times 96,500, we end up with a value of minus 212,300 joules. And that makes sense. We've got a positive cell potential. We very much need a negative delta G. Let's convert that into kilojoules because that's what we often need to do. Divide by 1,000, we get minus 212 kilojoules for our Gibbs-free energy, implying a spontaneous reaction. Delta G equals minus 212. Excellent, so let's put it all together now. All our tools in our metaphorical tool belt. Put together all elements by considering the common alkali battery. So I'm sure you got some of these lying around in your home. I got 2 half cells there. They're the common alkaline battery that I'm sure you're familiar with. We use them to power all sorts of useful gizmos and gadgets there. Mine are from Coles. They contain half cells. So we have this manganese oxide, and zinc oxide, zinc half cells. So these are very much contained within there in order to generate that electrical energy that we need. So here's what I want you to do. I want you to put together all the elements, a lot of the elements we've looked at in this unit, by doing the following for the alkaline battery. I want you to use the above information, write each half reaction, the overall reaction, the value of the cell potential, and the value of delta G using our nice new equation there. So a really good one to pause, consider all of those elements, and we'll go through it together now. So we've got to work out our 2 half reactions first of all. We've got to work out what's been oxidized and what's been reduced. So our more positive reduction potential will be driving the reduction reaction. It's the better oxidizing agent. The more negative will be driving the oxidation reaction. It's the better reducing agent. So let's go and rewrite these equations over here in the correct directions. So let's start with the reduction reaction where we have this manganese species. So 2MnO2 solid, 2MnO2 solid, and that is reacting with, we got some water in there, and we've got 2 electrons. We'll keep it as an equilibrium there, and we're forming Mn2O3 aqueous, solid, Mn2O3 solid, and 2 hydroxide. And we have a cell potential, or rather a reduction potential more accurately, of 0.11 volts. So let's pop that there, 0.11 volts like that. Brilliant. Then we have the oxidation reaction, which we said is going to be this zinc reaction occurring in the backwards direction. So let's write out that, showing that. So we have the zinc solid, and we have the hydroxide aqueous, and we're going to be forming the zinc oxide ZNO solid and H2O liquid. And we've got our oxidation reaction, so our 2 electrons on that side. So look, I'll pop that as a reduction potential. Let's pop this as an oxidation potential. So let's go ahead and flip our sign in that reverse direction. We've got to go from a minus 1.41, and that's going to become a plus 0.41, 1.41, because we're now talking about the oxidation potential. So there are our 2 half reactions. Let's go ahead and do an overall reaction now. So recall that when we're doing our overall reactions, we've got to get our electrons to cancel out. And in fact, if there's any other species that are remaining unchanged on our left-hand side and our right-hand side, well, we can cancel them out as well because our chemical reactions only show chemical changes. So our electrons are balanced already, so they can cancel out straight away. Look, we got a hydroxide there, and I think I've missed a... Yes, it should be 2 hydroxide. So let me pop a 2 there. So these 2 are going to cancel out there like that because they're going to remain chemically unchanged. It's 2 hydroxides on both sides. And then the same thing with our water over here. So H2O liquid, H2O liquid. Let's cancel that out because it's not chemically changing. And now let's just combine our half equations to get our overall reaction for the good old alkaline battery. So 2MnO2 solid plus zinc solid goes to Mn2O3 solid plus ZNO solid. And that there is going to be our overall reaction. Brilliant. So what now? Let's get some cell potentials going on. So we know that the cell potential is equal to the reduction potential plus an oxidation potential, where we've got the reduction potential there, which is plus 0.11, and then we're plussing it to our oxidation potential. I've already flipped my sign there because I've showed the oxidation reaction, so plus 1.41, and I can do this one in my head. That's going to be plus 1.52 volts, and that's the cell potential that we're generating. And in fact, if you look at my alkaline battery here, if I can get it to focus on that yellow ribbon, it is in fact 1.5 volts there. So all lining up. Let's do the last little bit, which is getting our delta G. So our delta G is going to be equal to minus N times by our cell potential times by our value for Faraday's constant. So how many electrons were transferred? Well, we've got, I forgot an aqueous here. We got 2 electrons being transferred, so minus 2 times by our cell potential, which we just got above, and then multiply by Faraday's constant, which is a constant, 96,500. We can plug all that in the calculator. I'm not going to do this one in my head. Minus 2 times 1.52 times 96,500. End up with minus 293,360 joules. Let's get this into kilojoules. Let's look at significant figures for this one. We've got 2 significant figures there. So let's give this 2 significant figures, minus 290 kilojoules, like so. Brilliant. And that should give us all of our answers here. So we got oxidation half reaction, reduction half reaction, overall reaction, cell potential, and a value for delta G. Brilliant. That concludes our look at spontaneity, Gibbs free energy, and cell potential. What did we do? We understood and used our equation there for delta G. As always, some tasks. Pause, consolidate, 1 column at a time from the bottom to top if you want some extra practice there. Fantastic. That concludes not only our lesson, but it concludes this series on electrochemistry. Thanks for joining me. Look forward to next time. We'll start something completely new. Have a good one. See you then. Bye.